Welcome to the second video in this Assistant Engineering Public Health Department Electrical Engineering 2024 paper solution playlist. In the previous video in this playlist, we discussed from question number 1 to question number 5. Today in this video, we will discuss from question number 6 to question number 10. Okay, so now let's see what question number 6 says. It says a resistance of 5 ohm is connected in a branch of a network. The current in this branch is 2 ampere. If this 5 ohm resistor is replaced by a 10 ohm resistor, the current in the branch will be. There are 4 options we need to choose from. The first option says maybe more or less than 2 ampere. Second option says will be more than 2 ampere. Third option says will be less than 2 ampere. And the final option says will be 2 ampere. Okay, now we will solve this question using Thevenin's theorem. We will represent the given network using Thevenin equivalent circuit, which consists of a Thevenin's voltage. This is the Thevenin's voltage, a Thevenin's resistance connected to a load resistance, Thevenin's resistance connected to a load resistance, and a load current. This would be the load current. So as we see two circuit diagrams here, in the first diagram of two circuit diagrams as in first circuit diagram and second circuit diagram. Okay, so in the first diagram, a 5 ohm load resistance is connected across terminals A and B through which a load current of 2 ampere, let's name it I1, is flowing. Now we know using Thevenin's theorem, load current is equal to Thevenin's voltage divided by the sum of Thevenin's resistance and load resistance. This is the formula we have from Thevenin's theorem, right? So in the first circuit, the value of RL, that is load resistance, is 5 ohm. This is the load resistance and the value is 5 ohm. So we will put the value of RL in the equation as 5 ohm and put the given value of IL, which is I1 equal to 2 ampere, and name the equation 1. So we did nothing. What we did was, we have this formula. We will just substitute the values. The RL value is 5 ampere. 5 ohm. Where did we get this from? From here. Then IL, load current value, is I1, which is equal to 2 ampere. IL is equal to I1, which is equal to 2 ampere. So we substituted the values, and what we did, we named this equation as equation 1. So after that, as given in the question, we will now replace the load resistance of 5 ohm with 10 ohm and name the load current flowing through the 10 ohm resistor as I2. So yeah, in the given question, it was said this load resistor was 5 ohm load resistor was replaced with 10 ohm load resistor. So we did that. We replaced it. And then the load current becomes I2 from I1. And after that, what we would do is, in the same way, we will put the value of RL equal to 10 ohm in the equation and I2 in place of load current. So see what we did. This was the formula. This was the main formula. We put in the first circuit, we substituted the values and named the equation 1. Similarly, in the second circuit, we will substitute the values and name the equation 2. We substituted what values? IL value, which is I2 here, and RL value, this value, which is 10 ohm here. Okay, now we have two equations, 1 and 2. We will compare both the equations in order to have our answer. So we have equations 1 and 2. We will compare both the equations in order to have our answer. Now tell me one thing. The denominator of I1 or I2, which one is bigger? Of course, right? Of course, the denominator of I2 is bigger because the RTH value stays constant. So if we add 10 in place of 5 to RTH, definitely RTH plus 10 will be greater than RTH plus 5. And we know greater is the denominator, lesser is the number, which means since the denominator of I2 is bigger, so the value of I2 will be smaller. That is, I1 greater than I2. Now from question, we have the value of I1 as 2 ampere. It was given in the question, right? The current in this branch is 2 ampere. This was the load current in the first case. So I1 value we have 2 ampere. So what we are going to do is we will substitute in this equation, okay? Then we will have I2 less than 2 ampere. I2 less than 2 ampere. We did nothing. We have I1 equal to 2 ampere. This was our equation, not equation. What do we say? Comparison. And here we will substitute the value of I1, that is 2 ampere. Then I2 will be less than 2 ampere. I2 will be less than 2 ampere. And hence we have our answer, which is option C, will be less than 2 ampere. Option C will be less than 2 ampere. This is the answer. I have not ticked here, just tick it. Okay, you can do that. Okay, now, all right, let's see what this question says. It says two incandescent light bulbs of 40 watt and 60 watt rating are connected in series across the mains. Then option A, the bulbs together consume 100 watt. Option B, the bulbs together consume 50 watt. Option C, the 60 watt bulb glows brighter. Option D, the 40 watt bulb glows brighter. Okay, so now we will make the circuit with the information given. We will connect two bulbs in series as shown, which will be further connected to a supply. One bulb is of 40 watt rating and the other bulb has a power rating of 60 watt. It's given in the question. See, 40 watt and 60 watt. Two incandescent light bulbs connected in series. We did that. And across the mains. Across the mains. Okay, we did this. Okay. Now we know current stays constant in a series connection. And we know current will depend on the resistance offered by the bulbs. The more the resistance a bulb has, the lesser will be the current flowing through it and vice versa, as resistance opposes the flow of current. Now we know power is equal to the product of current square and resistance. P is equal to I square R. Since this is a series connection, the current will stay constant and the power will hence become directly proportional to resistance. Since I is constant because of series connection, so I will become constant. So what will happen? In place of P equal to I square R, I square will act as a proportionality constant, hence making P directly proportional to R. Okay. Now between both bulbs, which one has a lower power? It's the one having 40 watt power, right? So using the P directly proportional to R proportionality, we can see the resistance offered by the 40 watt bulb is lesser than that by the 60 watt bulb. And we know more is the resistance, lesser is the current flow. So the 40 watt bulb will have a greater current flow as its resistance will be smaller. So more is the current flow, the brighter the bulb will glow. Hence, the 40 watt bulb will glow brighter. So now we have our answer. What is the answer? So the answer is option D. The 40 watt bulb glows brighter. This is the answer. D. Okay. What does question 8 say? It says a practical current source is usually represented by, we have four options again. Option A resistance in series with an ideal current source. Option B, a resistance in parallel with an ideal current source. Option C, a resistance in parallel with an ideal voltage source. And D, none of the above. Okay. So now what happens is, as you see from the circuit diagram, source, a practical current source is always equivalent to an ideal current source in parallel with a high resistance. Now, why high resistance? It is because so that no current bypasses through it, hence leaving all the current to pass through the current source. As you can see here, resistance, this is the parallel resistance. So this is the ideal current source, and both of these together comprise the practical current source. This is what happens. So the why high resistance? So that minimum or negligible current flows through here. So that there's no current bypass. So we have our answer, which is B, a resistance in parallel with an ideal current source. A resistance, a high resistance actually, in parallel with an ideal current source is called practical current source. Option B is the answer. Okay. So in this question, it's given a dead storage battery can be revived by. We have four options. Option A, a dose of sulfuric acid. Option B, adding so-called battery restorer. Option C, adding distilled water. Option D, none of the above. So what happens is, for the first option, a dead storage battery cannot, be revived by a dose of sulfuric acid because it will only cause more harm to the battery. So option A is not correct. Okay. Now moving to option B, adding so-called battery restorer might offer, a brief improvement, but it won't solve the root problem. And for option C, adding distilled water, it won't give the battery the necessary energy to function again. So we are left with only one option, and that is option D, none of the above, which is the correct answer. Okay, so now let's move on to question number 10. What does it say? It says in the given circuit, the initial capacitor voltage is 0. The switch is closed at time equal to 0. The final steady state voltage across the capacitor is. We have been given the circuit. We have four options to choose from. The answer is marked there. Let's find out how the answer is B, 50 volt. So now what happens is, in the first line, it's given the initial capacitor voltage is 0. So obviously the capacitor voltage will be 0 as the gate is not closed, or the switch is not closed. So it's open circuit, no current is flowing, and hence there is no voltage across the capacitor. And then it said the switch is closed at t equal to 0. So what happens is, this switch, it is closed. As soon as the switch is closed, current will start flowing in the circuit. So when the charge around or the charge across the capacitor changes, the voltage across the capacitor also changes. How? By the relation Q equal to CV. We know it, right? In a capacitor, we have the formula Q equal to CV. So as soon as Q changes, voltage across it also changes. And now what happens is, the voltage keeps on changing, and the capacitor keeps getting charged and charged and charged, and it will reach a point where it will be fully charged, and it will no longer get charged as it has reached its saturation level, and that phase would be called as steady state phase. And in that phase, the voltage would be called as steady state voltage. And in this question, we have been asked that the steady state voltage. So in steady state, the voltage across the capacitor will get fixed. So what will happen in steady state? The capacitor will no longer allow current to pass through it, and then it will behave as an open circuit. The capacitor, it will behave as an open circuit. So what will happen is, the voltage across the 10 microfarad capacitor will become equal to the voltage across the 10 ohm resistor. Not this 10 ohm resistor, the 10 ohm resistor on the right. Voltage across the capacitor will become equal to the voltage across the 10 ohm resistor on the right. We have it's written in steady state, the capacitor behaves as an open circuit. So steady state voltage across the capacitor will be equal to voltage across 10 ohm resistor on the right. Okay, so now what we need to do, we have found out. We need to find out the voltage across this resistor, 10 ohm resistor on the right, in order to have the final steady state voltage across the capacitor. So now finding the voltage across the 10 ohm resistor on the right will be very easy, because it's nothing but this circuit. This entire circuit has come down to this circuit. How? As I have said just now, in steady state, this capacitor will act as an open circuit, which is this. So we are only left with this, and the switch was already closed. It is said in this line only, this line itself. So it's closed circuit here and open circuit here. So we have this circuit to solve now in order to find our requisite voltage. Let's see how to solve. 10 ohm, 10 ohm, they're connected in series, and when resistances are connected in series, we add them up, we sum them up. So 10 plus 10 is equal to 20 ohm. We have 20 ohm resistance, we have 100 volt voltage, so we need to find out the current. So by Ohm's law, V is equal to IR, I equal to V by R, voltage is 100 and resistance will be equal to 10 plus 10. And when we calculate, we will get the value of I to be is equal to 5 ampere. So now see, this current equal to 5 ampere is across what? Is across this series combination of resistors. Now what happens is, in series combination, the current stays constant. So the 10 both the 10 ohm resistances will have the same current flowing through it, and that is 5 ampere. So also across this 10 ohm resistor on the right, we will have 5 ampere current flowing through it. But we needed the voltage, right? We needed the voltage. So to find out the voltage value, we have the current value, which is 5 ampere, and the resistance value, which is 10 ohm. So by using V equal to IR, we can easily now find out the voltage across this 10 ohm resistor. So the voltage across 10 ohm resistor, V is equal to IR. I is 5 ampere and R is 10 ohm, which is equal to 50 volt. And as we have seen in this equation, the voltage across 10 ohm resistor on the right is equal to voltage, steady state voltage across the capacitor, which was the requisite voltage. This is what we needed in the question. So this 50 volt will be equal to steady state voltage across the capacitor. So the answer is 50 volt, which is option B, 50 volt. Hence we have our answer. Thank you guys for watching this video. The next video will be dropped soon. So till then, stay tuned. Thank you.